What's going on, guys?
Hey there.
What are we working on in here?
Just setting everything up, getting all these configured and ready for the test. It's actually not that tough. I mean, yeah, there's a lot of mics here, obviously. We've got them all strewn about here. There's 60 of them. But it's really not that hard to set up. It's not that hard to configure. Using Wireless Manager, everything shows up in there, and you just go through and you can just identify which one's which and make the settings on them. So it's just sit down in front of the computer and roll with it. So.
Yeah, come on over here. Check this out.
Yeah, we'll do it.
So we currently have Wireless Manager open. We have all of our devices here in our device list, which we can rename, and we've given different device IDs so we can identify them a little bit more easily. And in our DECT link configuration tab here, we have all our devices, and some of these are going to go to our mix out on our ATDM 1012 DAN mixer that we have over here in our little portable equipment rack. And this is all set up. Pardon the mess, it's not dressed up yet, but we're validating everything right now, and next step will be making this all look nice, dressing it up, and getting ready to do what we're going to do on Thursday.
We're making some progress here. What do we have going on?
Well, actually, this is, I guess you could call it test run number 2. We had Dan came up here a few weeks ago to run a whole bunch of channels in the environment to see what was happening. Today we're setting up for the event, which is tomorrow. And you can see it's kind of deceiving. So you have right here and across these two shelves, there's actually 60 channels of microphones here running right now. They're all hot. They're all running. I can light off any one of these, and they're fired up, and there's audio going through the system on all of them. What's interesting about this is because we wanted to condense this all, because we've got everybody's going to be sitting here and presenting, and when to show it is that we've got these, of course, these white pieces here. These are the receivers. There's 8 of them, 4 on this side and 4 on that side. Typically, you really don't want to run your transmitters this close to a receiver because it has the potential of overloading things. But the reality is this is working just fine. It just talks about how robust of a system we have here, that it's able to handle it doing all this without a problem at all. And I actually earlier took one of the transmitters, went way back in the kitchen and tried to block it and make it cut off, and it wouldn't do it. So, they're all rock solid right now. We're just going to run the rest of the day and make sure everything stays the way it's supposed to, and then we set up tomorrow and we run it and we go with it.
Yeah, I think Jeff has my
He was just going to sweep them.
Right.
Pretty much. All right, well, this is a good time when you can get a kick off and get started. I want to thank you guys for coming down here. I know this is a little bit of a trek in getting here, as we were just talking about. It is exactly the easiest thing to do, getting in here. But I'm sure many of you weren't even aware of this was here. This is what we call Technica House. So this is Audio-Technica's little space here in New York City. where we really kind of showcase some of our really high-end audiophile stuff. And for some of you who may not be aware of this, of course, we make high-end turntables, high-end headphones, really high-end headphone amp. If you wanted to have a chance to hear what about $120,000 audio chain sounds through in headphones, make sure you get a chance to listen to that. It's actually pretty cool. It is. You can really hear those circuits. And that's the kind of thought that our engineering team puts into it. They're really looking at it from an audio spin first. They're really looking for that audio quality first. But, and so if you get a chance to check that out, that'd be cool. But that's not why we're here. And actually, interestingly enough, we're not just here because Audio-Technica has this cool space. We're here because we're talking about DECT systems. Digital Enhanced Cordless Telecommunication, they call it. It has had many different names in the past. But part of the reason I'm here in New York specifically is because DECT systems have been out for quite some time. Probably, well, for professional microphones, for all us and our competitors have been around for more than a dozen years. But what I've consistently heard, especially out of this area, in New York City specifically, is, hey, we can't use DECT because it doesn't work in the city. It doesn't work for this reason or that reason, the other reason. And that's all been pretty well understood. Our competitors, I most certainly throughout this process, when we talk about how we do things and how our competitors do things, I'm not knocking how anybody does it. They're just different ways that the technology is employed. And, so our competitors are very well aware, that these difficulties exist. The responses I had constantly heard from Chris and people saying is, I can't get more than 20 channels of DECT to work in New York City. After 20, they start bouncing and lights start flashing and everything. And, kind of a spoiler alert, next to me you see there are 60 channels of wireless sitting here, rock solid, and not dropping at all. And to make things a little bit more difficult, because I like to make things more difficult, you'll notice that the white pieces here, those are the receivers for it. And if you're not that familiar with RF, you really shouldn't have the transmitters that close to the receiver, because there's definitely a risk of overload. But it's not happening. It's actually running fine. And the mic I'm talking through right now that you can hear through this is actually one of the DECT microphones. It's well packed with but I can pick up randomly any one of these, and it's running. They're all running. The audio's coming through here. I can pick up the gooseneck microphones and talk through them. So these are all running. There's no mystery here, except that it works. But today, what we are going to do is we're going to go through all this. And we're going to talk about why. Why is it that our competitors or previous iterations of DECT equipment has had a difficult time working in this type of environment, in urban environments, and what technology we are employing so that we can deploy 60 channels right here. So that's what we're going to go through. Now, I feel free to ask a question at any point in time. And I'm looking at you because I know you're going to ask. Feel free to ask any. I'm kind of one of those free flow kind of guys. I'm not a rigid, must follow slide A, B, C, and D thing. So if we find something that is intriguing that we want to ask a question, please do so. Let me know and we'll dig into it, because the whole point today is to help you guys understand what's going on here and take a little bit of the mystery out of it. And so the urban areas is really where we have this difficulty. But I want to put it into a context a little bit more about the spectrum that we're talking about in the environment. In today's wireless, you have a lot of different spectrums you can operate in. You can operate in the UHF TV spectrum, which we're all very used to, which is that 470 to 608 megahertz. You've got, some of the ISM bands, like 2.4 gigahertz, where you have Wi-Fi, and then you have the DECT band. And the DECT band is, here in the US, it's 1.92 to 1.93 gigahertz. But there are a lot of different pluses and minuses to operating in all these different bands, and we're going to kind of go through the context. But one of the things I wanted to point out here is when we're talking about the urban areas like what we have here, you have a lot more challenges than you do out in the middle of Nebraska. Or in some of these, even some other urban areas, some other cities that are a little bit more sprawled out and things like that. It really has to do with population density. And you've walked, you can see those towers that are circled in red here. I mean, you can walk down any block here and just stop and turn and see 2 or 3 of these different other ones. And this is 5G and LTE, and I'm going to explain why that matters. But the whole thing is you've got so many people in such a dense area that all want to pick up their phones, and they need to receive phone calls, they need data, they need all that. And that's why they're here, and it's gotten worse and worse and worse, and isn't going to really get any better. You know, so this is part of one of the problems that we're faced with is all that, you know, excess RF that's occurring. And one of the things to understand about RF, people say, okay, well, I'm only worried about, I'm operating in this little frequency band. And that's cool, because that's all you're really focusing on. But the more RF energy that exists within the entire spectrum, the higher your noise floor goes across the higher spectrum. So even though you may have filters and you might have it so that you're only trying to receive in this area, that noise floor is still going to be higher. It's still going to be more to deal with because there's just so much additional energy that's going through the air. So we're also going to talk about DECT system, how the structure works, modulation. We're going to talk a little bit about some RF amplifier and engineering thoughts and how we engineered our system, and you know how typical things work with these different DECT systems. So we're going to dig into some pretty good detail, and then we're going to talk about some of the benefits in the way that we're doing things and how that's going to work out well for them. So that picture you saw that I had this is scaled back a little bit. This is not an accidental shot. So the red rectangle there in the lower left, that's these 4 windows. All right. And so just on top of this building that we're in right now, you've got 2 towers just right on top of that. So, you know what, 100 yards that way, there's a bunch of towers. And also, actually, if you look at this, kind of pan to the right a little bit, across the street on the corner right down here is another one. But that cluster is actually considerably lower in elevation. And so what you end up having is buildings like this where you've just got energy that is basically blasting right through your windows. So let's talk a little bit about what we're dealing with for that spectrum and just what we have here. So one of the reasons that people have chosen DECT, one of the reasons DECT is a good idea is it is a relatively, and we'll get into the relative side, stable RF environment. All right, so DECT is actually a fairly well-controlled environment because you have to play by certain rules in order to operate there. You know, I can't just go out and make, you know, a traditional handheld wireless that has 1 channel and decide I'm going to tune it to that frequency. No, there are some limitations that are in that band. So we all have to play by the rules, which actually, in most cases, works out fine. That's great. Well-controlled environment, everything coordinates, and that's fine. So, and 1.9 gigahertz is actually a really good balance. So, in some of the lower frequencies, like your UHF TV, or if you're going down to VHF and some of your other wireless, some wireless, you get a lot of distance. That signal can bend around objects very well. It can go through objects very well. So if you have very large areas that, hey, you have to deal with, that's the right choice. But sometimes you really don't want that distance. Sometimes you want to contain that energy within a space because maybe you're doing a building that has a bunch of channels that are in use here and a bunch of channels in use in the floor above and below. So getting into that little bit higher frequency really does help contain that, and it's a good balance. And when you go up a little bit further, and I know this isn't a session talking about our System 20 technology, our Wi-Fi technology, Wi-Fi band technology, but that has a much, much shorter range. If you can control your environment, place your antennas where you need to, that's one of those perfect things where I can just cover this space and I can kind of paste and repeat. We've seen it done in schools where they just do classroom here, next classroom, on and on and on. You can just go crazy with it, and it works really well like that because it confines that energy in there. But this 1.92, it can actually go a little bit further. It can actually penetrate objects a little bit better. In fact, the range that you can get out of the system in the standard mode, which is what I'm in now at 30 milliwatts, is 100 meters. You know, so you can actually get, it's a good balance. And you can get a high channel count. That's 48 channels in standard mode, 96 in high density mode. So you can get a lot of channels in there. And there's a lot of good reasons, obviously, you might want to do that. I will say, as we get into the frame structure, we'll see there are some trade-offs that you're going to do about that, or you're going to get for that. So DECT is actually a really good predictable band, but when you start getting into talking about where we are now, physically where we are now, this is where you start to see some potential problems. So this spectrum that you're seeing right here, it is the personal communication spectrum. This scan actually goes from 1.9 to 1.97, I believe it is. So it encompasses part of the PCS band, and then you see that gap in the middle, which is called the UPCS band, unlicensed personal communication system. That's the DECT band. So that little slot in the middle is the DECT band. But if you notice, right to the right of the DECT band, there's a pretty significant signal. That is 5G LTE. That's those towers I just had on those photos earlier, because this is physically was done in this room. So just on the upper edge of DECT, I've got significant RF energy. Now, if you're going to ask yourself, how much RF energy, how is it relatively speaking? Well, this is what it looks like in comparison to the DECT signal. So that's with, a measurement taken from this room with, in this case, actually 60 DECT channels running, and having that PCS. You can see relatively, yes, because I'm in the same room, that DECT is stronger, but not by a lot. That signal that's getting into this room from that 5G and LTE is pretty significant. And I'm going to talk a little bit about why that matters and how that becomes a problem. Because, even though it's not right in there, again, like I said, it raises the noise floor, but there's also energy that bleeds down into it from above. Filters are not perfect. So let's see. So let's talk a little bit about the architecture. So this is your frame structure. And every DECT device has to obey this kind of structure. You've got a 10 millisecond frame, and that frame has 24 slots. All right, and so it has 12 slots that are for download from your receiver to your transmitter, or as they would call handsets, because remember this was actually designed for cordless telephones. And then 12 uplink slots from that handset to the base station is how it's usually referred to. If you read the specs, they talk about handsets or mobile stations and base stations. That's what it was really designed for. And it's what they call a symmetrical slot allocation. And inside of them, you divide it up. It contains all this different stuff like your data. You're also, so like your A field, your B field. A is just network control. B is user data, which in our world is the audio data. And what I really want to also point out is the X field. So the X field, they call it transmission quality. What the X code really is, the X field really is that's error correction field. So that's where all your error correction data exists. So all those forward error correction data codes. So when the receiver gets all this data and they're comparing the the error correction data along with the actual data, they can tell if there was a lost bit of data, if you had your bit error rate. And it can actually, to a certain extent, can actually reconstruct lost data bits. But it all depends on just how many data bits you can fit in there. And that's kind of where you're restricted, because you only have so much time to do this on. Makes sense? Now that's the classic structure. But there is another one, they usually refer to that as classic DECT, but there's DECT, Cat IQ, and NG DECT, which is actually variations on a theme. And they still define that you have to 10 millisecond frames, and you repeat those frames every 10 milliseconds. But instead of saying you're stuck with 12 up and 12 down, they're telling you can shift that to an asymmetrical kind of format. That way, because in the case of microphones, I don't need a 1-for-1. I don't need 1 up, 1 down. So I can actually allocate more of those frames, more of those 12 slots within the frames, or actually 24 slots total. I can allocate more of those to uplink as opposed to down. So now I can start to see more channels. Now, another thing that is that's kind of a little bit of an engineering problem that's baked into DECT. It's something that, in theory, you have 12 up and 12 down slots, right? But whenever one of these receivers has to shift from an uplink to downlink, there's lost time. And they call it the blind spot, or actually sometimes referred to as a blind slot. Because if I've only have 10 milliseconds to work, and in the middle I need to shift from transmit to receive, there's going to be a section of that is unusable data. And so now, do I truly have 24 slots if I have a blind spot? The answer is no, you don't. And so that has been a kind of a classic little limitation in there. Now, it doesn't make much sense. Why would I mention that right now? Well, you'll see why I mention that, because it's one of the things that we address to try to make sure we get the most amount of data that we can into this structure. So, you know, there's just no useful payload within that time frame. So, by symmetrical slot allocation, a classic DECT is fine as it works, but it's just not very efficient for what we need to do. So when we go ahead and we can use some of those underutilized ones, and we can shift things over to have something kind of like this. So what we have here is this is an asymmetrical structure. And this is something that I would use in the standard mode. So the red ones, you notice they got two red dots. Maybe that's 2 frames that I can use, or slots, I gotta be careful about terminology. 2 slots that I can use for download information. But then the green one here, that would be microphone 1, and it's delivering its payload twice within that time frame. This is how you're getting the higher data rates out of standard definition as opposed to high density, excuse me. So your standard density, you're delivering 2 payloads. In your high density mode, when you're trying to get more channels, you're only delivering 1 of those payloads during that time. That's why when I go from standard density to high density, my data rates and all that get cut in half. This is exactly why that happens, because I only had 10 milliseconds to work. Now, let's see here. So, yeah, that's pretty clear. Do we have any questions so far? Yeah, I kind of wish I had a monitor in front of me, but I don't. So let's talk a little bit about modulation, and this is getting a little bit deeper in the weeds, but I think this is an important thing. So classic DECT states that there's only one type of modulation that you can use, and that's what they call Gaussian frequency shift keying, GFSK. And what that is it's a real simple, you know, if it's in one frequency, it's a 0. If it shifts its frequency slightly to another one, it's a 1. It shifts back and forth. It's one of the things about it, I mean, it's a fairly low data rate if you think about it, but it's also very reliable. You know, it's pretty easy for your RF amplifiers, are pretty inexpensive, and work really, really well. So it's what's called a constant envelope modulation. And what that means is it doesn't matter what your data package is, it's still modulating at full bandwidth. So you're going to get that full signal to noise every time. So it doesn't really, like I said, it doesn't matter what that information is. It's very robust when it comes to interference. It's very efficient, very simple kind of technology. But as we go through this, we're going to find out that there are some limitations. Now, one of those limitations has to do with this. They don't have to use very linear amplifiers. And this is, you know, a nonlinear amplifier versus a linear amplifier. So this chart kind of shows you what you have, where you on the bottom, you have the output, on the left side, you have the input. As the input goes up and the output goes up, when you start to approach the maximum, a nonlinear amplifier will begin to taper off, or in audio terms, it's compression. So that output starts to compress, all right, as it reaches that top. And what compression does whenever you do this, and anybody who is if anybody here's a musician, spends time with, you know, like 2 guitar amplifiers or anything like that, as you get into compression, so begins distortion. So you start getting harmonic distortion that fills things out. But it doesn't, you know, for most part though, you can make sure that you stay out of that nonlinear region when you're using these GFSKs, the simple ones. So you can choose a simple, inexpensive amplifier. It doesn't matter if it has that nonlinear region, you just stay below that. Make sense? That's simple enough. Now, this is what happens though when you exceed that. When you push an amplifier into its nonlinear region. Now, I had to emulate this using a spectrum analyzer. All right, and what I did was just a very simple case of proximity of the transmission and overloading the input or the power amplifier input stage of the spectrum analyzer. And you can see what happened. You can see on either side of the signal where all that noise came up. That's that extra garbage that is created because you drove that amplifier into its nonlinear signal. So whenever you get a signal that drives a power amplifier, whether that power amplifier is transmit or receive, when you drive that into nonlinear region, you create extra noise. So keep that part in mind for a moment. Because all of this is kind of, there's many moving parts as to why all this works. So that's one part, so keep that in mind. We're going to circle back to that. Now, the newer versions, or the alternative versions of DECT, the NG and IQ, CAT IQ, actually allow you to use different kinds of modulation. You can actually use phase shift keying. You can use binary or quadrature phase shift keying. Now, quadrature phase shift keying is where you're shifting your phase of your signal 4 times. You have 4 different values that you can shift that phase. And they can each represent a digit, a binary number. So now instead of just a 1 and a 0, I actually have 4. So I can do these different codes. And now I've effectively doubled my data rate. So to answer the question, which I actually heard earlier, when you compare Audio-Technica's DECT system, ours has data rates that's double that of our competitors. So to put that into perspective, in our standard mode, we're doing 128 kilobits per second, and in our high density, we're doing 64 kilobits per second. Looking at that frame that we talked about earlier, that makes perfect sense. Now, our competitors, they're using, in their high standard mode, they're at 64 kilobits per second, and they're at 32 kilobits per second in high density. And again, looking at that frame, you understand, but also looking at this, we're able to double the data because we're able to look at every cycle and look at a phase shift and determine, okay, what is that value? A 0 degree, 90 degree, 180, 270. This is for illustration, and I'll say this now before I get called out on it. QPSK, these things, it's not actually 0, 90, 180, it's actually offset by 45 degrees. So it's going to be 45 degrees, 135 degrees, and so on. But still, it can detect those different phase shifts on that.
It takes time to detect the phase shift, though.
It does. So it takes more than just time. It requires incredible linear accuracy.
That's right. Otherwise, this looks like garble.
It just looks like junk. So that's one of the things that we had to do. It needs to be accurate phase relationship and requires a linear amplifier. So this ties back to when you're using GFSK, who cares if it's a nonlinear amplifier? It's a 1 and it's a 0. It's one frequency or another. If it's distorted, who cares? Can't get away with that with this. So we've actually made it a little bit harder on ourselves by requiring something that has to use more complex circuitry, especially in that RF amplifier. So when we go back to this here with this amplifier curve here, we can't use an amplifier that has that high nonlinearity when you're looking for that phase differences. So this is the second part of it. So we start looking at these different things about, all right, my first, or maybe your first response would be, wait a minute, if you're using phase shifts and they're just using simple frequency shift, shouldn't yours be more susceptible to problems than the competition? And I would say, all things being equal, yeah, that could be a true statement. But there's more under the hood than that. And there's more involved in it, it's externally and internally. So we're going to talk about just what that all means and just how we manage this and how we solve these problems. So first of all, we're using a very, very linear amplifier. So one of the things about this, and some of you may have run into this with some 600 megahertz stuff, is that when you're using an amplifier that is nonlinear, out-of-band emissions can creep into your front end and actually overdrive. Now, I'll give you an example. So, and actually this happened in Reading, I believe, with one of Chris's customers. And this was, lower frequency, obviously, but what had happened is they were using this at church. They were using standard wireless, just typical UHF wireless. They had an RF distribution feeding, I think it was 8 channels of wireless, nothing fancy. Well, all of a sudden, he couldn't receive anything. He actually did a scan and said there were no free frequencies. Then he said, but if I hook an antenna directly to the receiver, it works fine. What was happening is they had just put a 5G antenna on the side of the building, and it was overloading the RF distribution amp. It drove its amplifiers into that nonlinear region and just saturated the whole thing, all that noise. So now, if I'm sitting in here with a nonlinear amplifier using one of my competitors' devices, which by the way, like I said, I'm not going to slam these guys. The stuff worked great. The technology is great. The circuitry that they use, which is common knowledge, if you really want to go to the FCC website and look up the FCC tests, you can actually see the photographs of the circuits. You can see the chips that are used. But what's happening is these out-of-band transmissions, like the antennas are up here, this 5G and LTE, is overloading the input stages. It's driving them into the nonlinear region, and then it's causing that saturation across the band. And so that distortion now lowers the sensitivity of that system. And so now this is why some of these other competitors have a difficult time in this kind of environment, is because they're just getting wiped out by all the extra energy. Now for us, because we're doing phase shift requires us to use more linear amplifiers, which means getting driven into that nonlinear region is less likely to happen. So, does that make sense? I know I'm pulling a lot of strings together here, connecting a lot of different things, but that's definitely one of the key things. And what looks like a disadvantage, actually, because we have to choose higher grade circuitry, it actually works out in our favor there. But that's not all there is. The linear RF amplification is part of it. The circuitry we have here, which the company that we used, the circuitry is a company called RTX. It makes it. Where our competitors use a chip from a company called Dialog, which you might have heard of Dialog. We use RTX. But it also has something that gets rid of that blind spot that we talked about. So that shift between uplink and downlink is actually going to 0. So now I actually have the full bandwidth to operate. And so I can have all that time in the 10 milliseconds to work. We also created something which I'm going to go into a little bit more detail. It's actually a patented trademark, the SheerWave technology from RTX, which actually is an adaptive channel equalization. And I'm going to explain that a little bit more because it sounds like a mouthful. And then of course there's active RF optimization in all this as well. Now one of the things I want to point out again here, I kind of glossed over it, is we've got double the amount of data that's going through because we're using that phase shift than our competitors do. And I talked to you about the X field, if you recall that field within the frame that contained error correction data. So the nice thing about that is not only do I have more data for higher data rate, being able to do 128 kilobits per second, I also have double the error data. So now I have a much more robust forward error correction by a lot. So even if we do get some of those distortions and we start ending up with some interference, we've got a much better forward error correction, so we can actually look at that and say, okay, we're missing data here, bits are missing there, and we can reconstruct that. So, a lot of things that lead to us being much better, better robust signal. That's what the RTX chip looks like if you really care. Yeah, exactly. Ooh, look at that. It looks like a chip. So, and so really what they've done though is they did the whole package. So RTX, like I said, they're a Dutch company, Danish company made in Denmark. So this whole chipset is actually a combination of a bunch of things. There's actually a dialogue chip in there, but then there's a lot of other advanced chips that they're using to do some of the RF chain and the nonlinear, or excuse me, very linear amplifier, plus they're talking about doing some of this other technology, and that 0 blind spot. And again, it's getting rid of that time frame, that loss, that missing data section between uplink and downlink. So here's what the SheerWave technology does, and this is really important here in how our system is able to deal with difficult environments. All right, so the SheerWave technology, the way that works is it's an adaptive RF equalizer. So if you look at this system here, you've got the transmitted signal, you've got a received signal that maybe is very, very distorted, and that's able to reconstruct that signal. You know, it's able to use a feedback loop that dynamically shifts its filtering so that it can recreate that signal as best as possible. I mean, there's certain things about the signal that are predictable, that you know are going to exist. So if I probably should have put another slide in here that had the timing on it again. But when you break that timing up, there's your control fields that are inside of each slot. This is known data. And since you know that your timing is 10 milliseconds from front to back, you know what your timing is supposed to be. So it's able to look at this and say, I know what it's supposed to be, and I know what I'm getting. And I can actually shift and equalize that so that I can change my signal to get and reconstruct the original. So again, I had said this earlier, I believe I said this to you earlier, it's all about timing. You know, when you know what your timing is and you know what certain pieces of data are supposed to be, you can use that to intelligently reconstruct your signal very easily. And so this is a continually adapted system, a constantly changing thing. And that happens not just from distortions created like in urban areas, like what we're talking about here, but that can also occur in highly reflective spaces. And actually, I would consider this is a highly reflective space. You know, we've got glass behind all these blinds here. We've got this brick. You can't see it, but behind here, this is all glass. But when you have all these reflective signals, you have signals that are arriving at different times, at slightly different times. And so it's going to come out and look all, again, these different times and cause these distortions, but it's able to get in there and again, figure out, because it knows the timing, what that signal's supposed to be. And so this is just kind of the path that it takes here. And, you know, your multiple reflection path or your distortion is causing phasing, or ISI, which is inter-symbol interference, and symbols being what your actual ones and zeros, your data is. And then it's able to deal with that and then adjust to reconstruct your signal. Another place that this actually works well, and I want to point this out because this is equally important, is in those distance applications where it's, you know, of course, the further away you get, the more reflections you get, the more out of time those are. And that's why we're able to get 100 meters out of this system at medium power without a problem. And actually, we have a high power mode if you really care to get, you want to get reckless, I guess you could call it. You can go to 100 milliwatts if you want to. And that's a lot of distance, it's a lot of range. But here's another thing that I hear all the time. Now, we have a mode in this system, it's called the roaming mode. What the roaming mode does is it allows me to take, let's just say, a handheld microphone, and let's just say it's assigned to this receiver right here. And I can actually mirror that on up to 5 different receivers. So what does that mean? Well, it means I could use this up here, then I could turn it, you know, go out of in the elevator, go up to another system on the 2nd floor that has one of those mirror ones, actually 3rd floor, and it would switch automatically. So once it leaves the proximity of this, the signal goes down to a certain level, it disconnects from that, and then when it gets in range of another one that is part of it, it connects to that. So it's actually one of those things that an instructor, and like if I'm going from here, I'm giving a lecture right now on this, and then let's just say at 5 o'clock I need to go upstairs and give a lecture on the sushi machine, I don't know, whatever. See, I can actually do that, walk out, go up there, and I don't have to do anything. And the roaming mode is somewhat unique. But the reason I point that out is because I always get the question, they say, hey, can I use that for divisible spaces? Now there's a reason I get that question. The reason I get that question is because the competitors using some of this simpler technology can't do divisible spaces very well. These reflections cause problems. They cause dropouts. And when you put divisible walls in there, you're just increasing the reflection problem. Believe it or not, those divisible walls really don't attenuate the signal very much, but the physical construction within them actually causes more reflections. And that makes that multipath a problem. But, as you see here, multipath is taken care of with this SheerWave thing. So when somebody comes to me and says, oh, can I use that roaming mode for divisible space? My answer is going to be no, because you don't need it. If I've got a ballroom that's 600 feet end to end, and I want to divide that up into 3 spaces so that I can, do it in Dante. Put all the receivers in one place, right in the middle, and let it do its thing. It will receive it fine. Change your routing in Dante, and that's all you need to do. That way you don't have to worry about somebody saying, all right, well, let me take this transmitter and put it in the charger, repair, none of that. You don't need to do any of it. It's much, much simpler. So, makes sense? I know the divisible room question is one we get quite a bit.
Well, I have a question.
Sir, go for it.
So what if you are, your belt packed up, you go up to the 3rd floor, and then when you're on the 3rd floor, you take the belt pack off. Can it permanently stay up there?
Yes, absolutely. So the question being is, if I have a belt pack paired in room A or floor 2, and I decide I'm going to go up to floor 3, and I just want to stay there. Absolutely, you can do that. It can stay in one room or the other forever and ever and ever. We've had some applications for roaming. One of the ones most notably was a courtroom application. I had courtrooms where they had 4 channels in each of these 3 courtrooms. And for the majority of the time, that's how they stayed. But if they needed to, they wanted to be able to bring more microphones into one room. But the reality is they don't have to live in any specific room. That transmitter doesn't. It's no longer assigned to one receive point. It's assigned to any of the 5 that you want. And so it can live whichever one you want. So in this case where you're worried about it, it's like, well, do I have to make sure that my end user returns that transmitter to? You don't. It can be in any one of those 5 locations and it can live there for as long as you want.
But you're still managing that with the signal routing, Dante, for instance.
You would. You'd be doing it. Typically, I would see it being done through your DSP. So if you're using biamp or QSys or whatever, it's going to come. What you're going to end up happening is that if this belt pack is assigned to Dante channel 1 on the receiver on this floor, when it changes to 1, it's going to be on Dante channel 1 on that one as well. So you're just looking, even if you have the same DSP that's managing both, you know that it's going to be an either or. It's never going to be an and. You're never going to be having that channel present on all of them. It's only going to be on one at a time. So you just manage all that routing through your DSP.
Well, the courtrooms and the classrooms are much the same because they're repeating their RF spectrum over and over again.
Yep. Over and over and over and over. Ad nauseum, I think. So, yeah, absolutely.
It's just been re-registered on the receiver on the 3rd floor.
Yeah, when it does that, the nice thing is it does that by itself.
My
So-
intercoms love it.
Yeah. So, yeah, makes it very simple. Good question, Ian.
Yeah, for the NPR space, you mentioned putting them all in one area. I guess 2 questions. One is it a plenum rated device? So you can put it above the ceiling?
So it's not a plenum rated device. So that it's very much like a wireless access point where, and the reason being is because a lot of plenum spaces, especially when you have like acoustic tile, they're foil backed. A lot of those are foil backed tiles for the fire rating, and that doesn't get along with RF very well. Now, if you need to hide it, there are plenty of back boxes made by any number of electrical companies that are plastic or RF invisible, as it were, that can recess those into ceilings or walls and things like that. So, it looks, well, you can see it looks exactly like a Wi-Fi access point, a little bit bigger than that. And most of the time people, just kind of ignore that. But if I had to, if they said, look, I can't do this, you could certainly recess that into something.
So it'd be like flush mounted with the ceiling?
Right, so you could. It's an omnidirectional, so it doesn't really matter its orientation.
Okay, that's my next question. And then are they daisy chained together?
They're not. It's Dante home run. They're run on PoE, so there's no daisy chaining. Now, technically, you do have the ability with Dante to do daisy chaining, but there's a couple of restrictions about that. One, the daisy chain using Dante card is a hop. It's another hop on Dante. So if you do a whole bunch, it can be a problem. And the second, you really can't pass PoE through a daisy chain like that. You can run into too many limitations and problems with power. And this is the only way it's powered. So they would need to each be home run.
Okay, and they're pretty close together in this configuration for the demo. And typically in a deployment, is there optimal spacing between them?
As far as the receive antennas, no. I think that's going to come down more to aesthetics than anything else. Do you like the symmetry of them spread out, or do you want to put them all close together? It doesn't really care because it's a timing-based system, and it manages all that. Another thing that DECT does, which we really didn't talk about, is it also has between each of these frames that it's transmitting and all that, it has what's called an RSSI frame, which is a received signal strength indicator, which is where it listens to what's going on, so that it can choose the correct timing and the correct frequency for everything. So it knows everybody around it. And so having them close together is really not going to cause a conflict. They're going to, you know, once you fire everything up and everything has its rhythm, it gets into the rhythm and it's fine. And again, that kind of proves just by how close these things are here right now. So really, when you're mounting these things, whatever fits the space, physically, aesthetically, you know, however you want to do it is not a problem.
If you do encounter interference, is it audible when it does the shifting, or is that something that just happens behind the scenes?
It all happens behind the scenes because, so to back up half a second, of course we got the 24 slots, right? Now I'm not using all 24 slots because I got a couple of download slots, and they didn't want me to talk about just how many slots or what, but we'll just say, let's say theoretically, out of the 24 slots, we got 2 of them that are download, and that leaves 22 slots left, right? Now what you have in DECT, by its definitions, you have not only that 10 millisecond frame, but you have 5 frequencies. And so if I had within that 22 times 5, that's 110 possible slots that I could run into in high density. Now we call it, when we say what's our max, we say 96 channels. That's for headroom purposes. And that's for that exact thing, to be able to ship things around, to be able to deal with it if you've got interference that it's catching. It's getting another signal that's coming in. It's basically, we don't want to get caught with a musical chairs where nobody's got something to sit down. We have the space to operate in. And so it's going to be able to manage itself. Would you hear it? No, because remember, all this is 24, you've got 24 frames or slots within a frame. That frame's only 10 milliseconds. And within the slot, how much of that is actual audio data is very, very little. It's very, very fast, and it's got data correction. You'll never hear it. You'll never hear it change. Even if you dropped just one packet, one slot, you'll never hear that. What starts to be a problem is when it loses its connection over a series of frames, and it can't find itself anymore. You know, the receiver, the transmitter starts trying to hunt for what it needs to be on, the receiver's trying to hunt for what's going on, and it just can't find it. But that takes time to happen. But I think we've all probably witnessed that before. What would start happening is you'd start seeing that light flash. That's it saying, I'm lost. And then it'll reconnect. But the tiny little things, you'll never hear. Make sense? I remember where we are. So you got a lot of extra performance that you're getting out of that. You're able to deal with things in the crowded RF environment because of those circuitry, because of all that's going on. You know, improved reception through distance and through different materials. And of course, you've got that enhanced data correction, which is really helping you out. And that's going to allow you to operate in that UPCS band. You know, so we understand that the classic DECT has some limitations, but using the more advanced versions of DECT, using the advanced RF technologies that we have, we're able to actually survive in a condition or in an environment where, you know, some of our competitors, as well as they do things, I don't want to knock it again, just have a difficult time. They struggle. And to give you an idea just how did we come about, how did this whole thing come about, this is kind of going off a little bit, but I'll let you know, is of course we heard from people, especially here in the New York City area, of what kind of problems that existed with DECT. But we actually ran into a very similar situation very close to home for us. So our headquarters, ATUS's headquarters in Still, Ohio, you know, half hour or so south of Cleveland. And we had a large client in Cleveland that I'm not allowed to talk about. We weren't even allowed to take pictures in their facility, you know, for fear of getting any pictures that could be recognized of where we were. But they said, hey, look, we've got 2 rooms, 32 channels each room. We can't make this work. You know, we fire them all up, they work for a minute, and then they just crash. They all start flashing, and they come back up. And then they crash, and they all go out. And we said, all right, well, let's go up there and do some scans and some tests. So we actually took up 64 channels of our system in the exact same environment, exact same positioning of antennas, and ours worked. Which is great, but we had to figure out why. And that's when we started doing the scans, and that's also when we noticed, looking out the window of the 10th floor of this building in downtown Cleveland, we're like, look, an antenna, and it was right there, facing right at us. And that's how we figured out that this was occurring. And then we started getting calls from other people. We had our territory manager for the East Coast had some guy in Miami, very similar problem, complaints from here in New York. And that's when we went in digging deeper on, what is causing the problem and why is it that this system can function. Now I know that the question has been asked, I had the question before we started this, is we've had customers who have said, hey, we had our system work until another client moved in on the room or moved into the space, and then actually everything fell apart at that point. Does that explain things? Well, there's a couple of things that could explain it. All right, one is, you're raising the noise floor every time you bring objects into a room. Every time you bring, and we all have cell phones here on us, I'm sure, this is raising the noise floor. All of that is going. Plus, there are many companies who these days, especially in urban areas, will spend the money to put cell phone repeater antennas into their spaces so that they can all have access to their phones. Maybe in a building, they're having a difficult time getting a signal, they'll put those boosters and things in a space. This creates problems. They could have a lot of other DECT things in there, but typically DECT like headsets, right? So, well, first thing, DECT of course was designed for telephones. That's what it used to be, digital enhanced cordless telephone. That's what it stood for until they changed the terminology of it. But, there were a lot of call centers using like DECT headsets. Well, that's not too many, but that's not a very popular system anymore. Mainly because Bluetooth is so much easier to deal with. Bluetooth is cheaper, batteries in those little headsets last longer, it's much easier to pair and connect. So most of those call centers moved over to Bluetooth. But even if the ones that had the DECT type of headset, we're not talking high power here. They're intentionally low power because they don't have to go very far. But they can still raise that noise floor. They can still cause intersymbol interference. They can still cause a little bit extra garbage to get into your spectrum. And the name of the game, signal to noise, always. So we have the ability to deal with that. We have the ability to reconstruct the signal, to get that better signal to noise. We have the ability to navigate around all these other things, and the ability to avoid that distortion that comes from just a flood of garbage coming into the front end. So that makes it a significantly different approach to how DECT is used with Audio-Technica as opposed to some of our competitors.
Are you dynamically adjusting the transmit power level?
No, actually that's interesting because that technically is something that you can do, but we're not. We don't. It wasn't necessary. And one of the things that you have to watch about that, weighing it in, so the question being is, can you dynamically, or can we dynamically change that power level? The questionnaire being, of course, around, well, if I needed a little higher signal noise, can I bump that power up a little bit? So technically you can do that, but you have to balance that against needs. And if your needs are, I have a big facility, I have a school, I have whatever, a courtroom, and I'm actually multiple rooms doing it, having adaptive power might get you in trouble. And especially if you have roaming in place where you're trying to take a transmitter from one room to the other, as you get further away, and it boosts the power on one of those, come back kind of things, and you never disconnect. So yeah, we just don't employ that variable power. So
Filtering?
filtering, there's always going to be filtering in place. So the front end of every receiver, and that includes our competitors, is always going to have filtering. But filtering is not perfect. All right, there's no such thing outside of a lab as a full drop filter that just does a cliff cutoff of a frequency. There's always going to be whatever dB per octave kind of slope. Of course, you don't say per octave in the RF world, but whatever your dB slope is, you're down, down 3, 6, and 10 dB points. But filters are not perfect. So there's still going to be, when you have these two bands, the PCS band and the licensed PCS band and unlicensed band, just that close together, even with filters, you're gonna have noise that's gonna come in there. It's just unavoidable. Now, in most circumstances, like I said, if I'm in St. Louis or something like that, they're fine. They filter out enough, but I have so many transmitters that are so nearby that that amount of noise just keeps getting higher and higher.
I also don't think the noise is steady state, it's dynamic, and you can have sudden emergence of harmonics and things that come and go, and you have to react to that instantaneously.
So it's interesting you should mention that, because we witnessed that in Cleveland, where and I just said where the competitor system had 32 channels that was running, and then all of a sudden they wouldn't. And it wasn't entirely predictable. It wasn't like it was a cycle, that it was occurring every 12 seconds or something like that. It was very unpredictable. And so you're right, it can be cyclical depending on just what's connecting to that specific closer radio tower, and then it has higher levels. And it can be very deceiving, where everything seems like it's working fine, and then everything just falls apart.
But this is where we don't want to roll a truck to come back up because something
Right.
temporary happened.
Right. And that's why you got to look at things and you got to say, hey man, what tools can I put in place? Because, you know, certainly you have a lot of options when you look at that. But if I say, all right, I've got a building that I need 32 channels in 4 different rooms, and I need it to be managing its own frequencies and automatic, you don't have a lot of choices. There are not a lot of choices. So you really have to look at it and say, what system out there is employing technology in the best way to try to make sure this works? Now, one of the nice things about the way our system is set up is I can walk into a space with one of these receivers, a PoE switch, and I can scan the room. This is where I volunteer Chris. Chris will scan the room for you. So,
I'll scan the room for you.
and what you what it does is it goes into the receive mode, right? And you can actually time, you can put it on time test. So I can sit there and say, I'm gonna let this thing run for hours. And it'll give you an average
You get
and
a
a
time
peak.
average.
Yeah, it'll say, all right, this is your average. You can do, you know, this many channels in standard mode, this many channels in high density mode, and then you can do the peak hold, which will show you basically an inverse. It'll show you the minimum number of channels that you can do. So, you know, if you're really looking at something and say, you know, I want an opportunity to find out what's going on over time in this space, you can absolutely do that with this system. And it'll tell you in real time or over time what you're able to deal with in that space. Now, I understand that a lot of you guys and anybody else have been burned. It happens, you know, and RF is one of those things where, you know, you can walk into a room acoustically and you can listen and you can look and I can say, I know this is going to be a reflection and that's going to be a bass trap and I can hear it. These are all easy things. You can't see it, you can't hear it. You don't know about RF being a problem until it's a problem. So, and too many times it's not a problem when you have a tech on site and they're doing the scans with whatever they're doing and they're setting it up and it's like, it worked when I was there. You know, actually that's why, you know, making sure you choose the right technology that was specifically designed to avoid the kind of problems that we're talking about, and the ability to go in there and do a scan and actually look at the environment over time to see what works. Make sense?
That scan, so that everything you do at the very beginning, and if you have a problem, could you also get continuously scan over time to see if things as like the environment changes?
Yeah, absolutely. So you can do a continuous scan on that. You can do basically a time scan. I don't have it set up on this computer right here, but what you would do is you could set it up and you could define the amount of time, or you just let it open run. So if I set a peak hold up and I let it run, it's going to peak hold for as long as you get it running. So if you put a PC, the little PoE switch in this in a room, and you run that, and you walk away for a weekend, as long as it's got power, it's going to keep it and log it. You know, have somebody roll in there on Friday, put it in, come back Monday, or the following Friday, or whatever, and it will have kept that log running. So. More questions? Pretty simple.
So what do you call red flags with this application?
Red flags with this application? I'm trying to think. I think, well, I guess it depends on what you consider a red flag. The one thing that I didn't mention at all has to do with the nature of DECT. And the nature of DECT is you've got a high latency system here. So I have had people say, this is just awesome, and look at the construction of these transmitters, and they sound great. Can I use these for performance? And it's at almost 17 milliseconds of latency in the standard mode, that ain't gonna work. So red flag is, I've got a church that wants to, time out, let's talk about the application. Because if you're doing performance, this is not gonna work. If you're doing spoken voice, it's even in the high density mode, which is 26 milliseconds of latency, well underneath the frame. You won't have any synchronization problems, so that's no big deal. Some red flags, Dan. By the way, this is Dan Pelletier as I interrupt him texting. Dan is
Texting my team.
He's an applications engineering team manager. Dan Pelletier here. And Dan, of course, he works. I'm the director of commercial applications. Dan manages the applications engineering team, and they get these calls all the time. So, Dan, what would you say if there's any red flags if somebody calls and says they're trying to do something that would make you hesitate about using the DECT system, aside from like latency?
Well, I mean, we prove our work. So, obviously red flags are dropouts. You don't want to experience dropouts, right? So, having a receiver on site to be able to run the scan and tell you how many you can get, we try to mitigate that risk on the front end, right? Because that's the ultimate red flag. In terms of operational use, though, Mark has mentioned that we always try to make sure that the noise floor is kept at an optimal level. And right now with receivers and the transmitters that are all right next to each other,
It's not optimal.
it's not optimal.
This would be a red flag, actually.
Red flag. So yeah, we would look for any other emitter. Wi-Fi in and of itself is not a red flag, but for me, I'd rather stay on the safe side and keep, any emitter a little further away. But in and of itself, it's not exactly a red flag.
So that's actually a good point, because you had asked me earlier about mounting these close together. And because these things are all on the same frequency, and because they're in DECT, they all have to play by the same rules, and they can detect each other's timing, they're fine. But Wi-Fi device there doesn't care what DECT is. Now, it's not in the same frequency band, but the same rules still apply. It's just outside of the band, and it could technically cause some problems. If, like, for example, that's a pretty simple access point there, but I'm sure we've all seen the pretty heavy-duty industrial ones in some of these facilities that are very high power. Probably don't want to mount something next to that. I would say, in my opinion, try to keep at least 10 feet away from it. So.
What happens if someone rolls through with like a Bolero intercom system or something? I mean, it would
Again,
be totally different. That's a performance space. This isn't a performance space.
well, I mean,
This is underneath or this is some classrooms above an auditorium.
right. I think, again, this is going to come down to knowing where your transmitters and receivers are. Because the transmitters have been tending to be a little on the higher end of the power scale, and then your receivers have to necessarily be much more sensitive. And it's analogous to setting up gain for an audio channel. I've set this up so that, maybe I'm using this handheld and I'm doing the typical ice cream cone thing that we all know our clients do, and I set that gain up so that this gives you a good volume. And then somebody jumps in and just bites right into it. This is very similar in that if you have a signal that's a little bit too strong for that gain path, it could overload it. It could cause problems. Filters only go so far, especially if the power's high enough. So it's one of those things. I would say anytime you're talking about how well does this system, and I would apply this to any system, by the way, this rules, how well will this system play with other systems in, always watch where your transmits and receive are. Just like in a live performance, I would say watch where your IEM antenna is versus your receive microphone antenna. Very similar kind of thing. I did talk a little longer than I thought.
Great job.
Thank you.
Thanks, Mark.
I appreciate everybody coming. I really did.
Please eat and drink.
Yeah.
Come out, chat with us friends.
All right, man. Let's go. It was fun last night, man. I enjoyed that.
Yeah, it was fun.
We'll do shoulders to get back. It'll be fun.
Technica House, New York, ESW presentation. Any initial thoughts?
The space was incredible. I mean, great venue for something like this. I mean, first time here, didn't even know the space existed. But for me to see 60 channels operating flawlessly for 2 hours with no drops, no reconnects, not a single hiccup, in such close proximity, transmitters, receiver all together was really impressive. I mean, I've never ever seen a system be able to do that before anywhere, let alone in an RF environment as hostile as this one. I mean, literally, as Mark showed, with the antennas being so close, really impressive, really impressive. I have seen applications and been a part of applications and designs myself where we had a much lower channel count be completely disrupted by a transmitter and tower and an antenna array that was considerably farther away than these are here, as he illustrated. So that to me was an eye-opener. That was an aha moment of, wow, we can do this wirelessly. Just the fact that we've had so many systems in the DECT band fail, or from what we have seen from competitors' applications and competitors' products, to see proof that technology can work if implemented correctly, was really impressive, because a lot of people, I think, had written it off as being not feasible, just not a viable solution for a lot of these higher channel count applications. And to see it work in real time, it's a huge addition to a lot of people's toolboxes, to their applications toolboxes, to be able to solve a problem, to meet a client's functional expectation, was a huge eye opener for me. So, from an application standpoint, to previous projects and systems that were designed using wireless products that lived in the DECT band, that initially worked fine. Met expectations, functionally everything was working, and then over time, as fewer and fewer channels were able to connect and stay connected in those environments, there was really no immediate solution available at that time for those clients who really wanted wireless functionality, who wanted the wireless flexibility to be able to place devices in their space wherever they needed them and take them up and redeploy them as different applications and different meeting formats presented themselves. That was a real disappointment for a lot of those clients, and to be able to now go back to a lot of them and say, we have a solution for that. You can meet your functional expectations. The system will work exactly as you want it to work in your environment, in your workflow, and know confidently that it will stay connected and be a robust solution without any hiccups or any potential points of failure. To be able to go back to them with a solution that works, it not only speaks to the evolution of the technology and the robustness of this product, but it also helps bridge the gap, I think, in some of those relationships where we proposed the solution initially based on what you needed and it failed. I think there was an erosion in confidence that we can now restore by coming back to them with a product and a technology that does work and works very, very robustly and very consistently. I think the transparency of saying that we have all these different options available in terms of output power and having the capability to crush everything in the room, but not needing to, because of how advanced the technology is, that we don't have to employ this hammer mentality, I think speaks volumes to the thoughtfulness of the engineering process and the design to say, hey, yes, we can crush everything, but just because we can doesn't mean we should. We solve our own problems at the expense of creating problems for others. But the technology is advanced enough in that we don't need to do that. We can actually do it in a smarter, better, more responsible way. One of the applications we see in tight urban environments like this consistently is in multi-floor spaces where we may have a very high channel count wireless deployment on one floor and a mirrored deployment directly above it and directly above it and directly below it. The fact that the system is intelligent enough to manage that, and you have all of the different output power options and settings, roaming mode to accommodate for transmitters leaving one space and ending up in another. I mean, we have flexibility that we've never ever seen before with this kind of technology. And to be able to come into a really hostile urban RF environment like this, multi-floor, multiple systems directly on top of each other, all kinds of outside factors like the antennas across the street and on top of this very building, to be able to manage all of that is really groundbreaking, because we've never been able to do that before. So there was really no answer to those clients who wanted a very specific experience, a very specific functional expectation, and not being able to deliver on it before now is a huge moment.
Yeah, so I think there's a few things that come to mind for that. One is that when we have some challenging situations, we tend to look at what the spectrum is in the area, just kind of based on any tools that are available for the manufacturer, and the client's expectations, their own experiences in that space. Typically, there's a variance between refreshes versus new builds, and what's worked and what hasn't worked, and of course that changes over time. Typically, the way we work in the consulting world is that part of the requirement is to have the AV integrators that we work with provide site surveys, frequency surveys before deployment, but we tend to specify microphones, wireless microphone systems based on what should work, based on what we know about the available spectrum. Sometimes we'll leverage support from manufacturers for that purpose, and then beyond that, I mean, I think it really comes down to being able to pivot as needed throughout the actual installation to do those surveys, make sure that things are working well, and be able to adjust. I think the benefit of this system is that it seems like there's a lot of flexibility that's inherent in the system, and the ability to adapt to, I guess, more challenging environments like a multi-purpose room, which is also kind of nice. I think beyond that, I think the other thing I liked about it was the ability for example, a multi-purpose room that you could have multiple antennas kind of in a central location, and expand coverage from there up to about 100 meters, which is very useful, and certainly something we don't see very often for wireless applications. Yeah, I think for sure. I'm thinking of some projects I'm actually working on now where I think it would be the DECT band would be an option. Typically, what we see is that there's the standard frequencies you expect from most wireless microphone providers, and then the DECT band I think is interesting because there's kind of where in my mind it would be nice to compete would be against microphones that are more of like the network-based solutions. I think that's the interesting thing. I think the other thing that I thought was very interesting was the leveraging of a microphone receiver that had a built-in microphone element, but the ability to add an element to make it a lavalier, which is also pretty intriguing. I thought what that was intriguing too is the ability to move the microphone from space to space. The flexibility of being able to do that. I believe it was 4 or 5 spaces, if memory serves, that you can move it from through receivers.
Yeah.
you know, I think it's great for ad hoc situations or for spaces that are, you know, constantly in flux, right? That you can share resources, have pooled resources, which is incredibly useful and cost effective. I think the overall experience was very informative. Definitely would like to get more information so we can delve in with our team in general for various projects as they come up. I think I guess the things I like about it, the form factor, the wireless kind of access point type form factor is nice, since that's, you know, everyone's comfortable with WAPs at this point and they expect them, versus sometimes, you know, you have to hide elements above ceilings and so forth, right, for microphones. I think the other thing about it that is nice is that it also is scalable, in that, you know, you have a situation where you need a certain number of microphones. It's nice that you can add like these additional access points, and, you know, and still have up to, I believe, 48 in standard mode, 96 in the high density mode, which is, I think, very promising. So I think that's another feature that I think is also very nice.
Awesome.